Welcome students. In today's class we will learn about the data flow optimization in high level synthesis. So, data flow is a very important optimizations in high level synthesis in which there are multiple functions which can run in parallel in hardware. Okay. So, let us try to understand what is that. So, let us take an example here. Say suppose you have written a program where you have this say main. So, in usually in high level synthesis main is the test bench. So, let us say this is my top level function which is say taking A as an input and say it is calling a function which sending function 1 sending A and function 1 is producing B. Okay. Then you are calling function 2 with B and you are producing C, right. And then you are calling function 3 where you are sending C and producing D. Okay. And there are many other part in the code as well. So, in this case whenever there is a function 1 which is consuming something producing something and then function 2 which is consuming the data which is produced by function 1 and producing something which is C which is consumed by function 3 and producing D, right. So, this is there is a producer consumer relation, right. So, this is very important term called producer consumer relation. This is very important, and the second thing is a feed forward data, right. Because there is no backage, right. So, it is basically in one way traffic. So, function 1 to function 2, function 2 to function 3. So, if this kind of behavior you have in some application, right. So, then if you think about its execution in C, so it will complete the execution of function 1 and let us say this A, B, C, D all are kind of array and there are big loops is happening there, right. In general it is happening say and then say function 1 say is taking say 100 cycle. Okay. Then the function 1 will be completed, then I am going to go to function 2 and then I am going to execute function 3, right. So, let us say function 2 takes say 50 cycle and then function 3 is taking say 100 cycle again. So, what all execution time will be 250 cycles. This is addition of this because it will execute one by one sequentially. Since there is a producer consumer relations, can I run these particular functions in parallel, right. So, that is something is the data flow and this data flow optimizations actually makes sure is going to happen that. Let us try to understand why, how. Okay. So, as we understand that this this function 1, this is my function 1, this is function 2 and this is function 3 the way I have explained, right. So, A is coming here, B is getting produced, C is coming here and D is getting output, right. This is the flow. So, what I understand that since this function 2 consuming the data B or say array B which is produced by F1, so function 1 has to wait, right, until this B is getting produced. That is why the sequential nature is coming. So, now what about, but it may be that this since it is running in loop and then this I do not need to wait for the complete production of the whole data A, say B this B may be a array of say 100 size 100, right. So, there are 100 data to be produced by function 1, but this function 2 may not need to wait for all 100 data to be produced, right. So, in general say A B 0 is produced, right. So, first data is produced and this function 2 can take V 0 and process that data. So, there are some function written in function 2 which is take B and produce say B 0 and produce C 0, right. So, the point I am trying to say is that whenever some data is getting produced in function 1, immediately function 2 can start processing that data, right, and that is what will enable. So, if we can enable that process, then what is going to happen? I do not need to put this function to wait till the complete the B is getting produced, right. So, this is this data flow optimization creates some hardware which makes sure that now this function 1, 2 and 3 can run in parallel. Obviously, they follow the producer consumer relations. So, and basically whenever there is some intermediate data get produced, immediately this function 2 can start working on that, right. That is what is the data flow optimization is all about, and let us see how we can enable that things in hardware, right. So, basically here we have to make this run function 1, function 2 and function 3 independently without with some handshaking to each other, right, with some synchronization. So, it is not, so as a result what the basic idea is that you add a channel between the function 1 and function 2. So, you implement this function 1 as a module and you implement function 2 as a module, right, because function gets mapped to some different module in hardware, and you add a channel. Channel is nothing but some memory, right. So, I will come into that the kind of type of channel we can support here. So, I am going to just put some memory here between process 1 and so this function 1 map to process 1 and function 2 map to process 2. Okay. So, now I am going to do is that I am going to add a memory in between, right. So, buffer is some memory, it can be RAM, FIFO, we are come to, I will come to that point. So, what is going to happen here is now process 1 which is equivalent to function 1 produce the data, say it is produce the B in the order like B0, B1, B2, B3 and so on. So, whenever B0 gets produced, B0 will come here, and immediately this process understand there are some data came, and there will be some way to check whether some data is available or not. Whenever it found that B0 is consumed, so it can now process B0 and produce C0, and it will also be stored in some buffer here, right. And then say next clock, this process B is now writing B1 to this memory, and in the next clock this process 2 understand B1 is now available. So, it will now take this B1, process it and produce C1, and it is getting written here. And similarly, process 3 now, which know that this C0 is available in earlier cycle, it now can take C0 and it can produce D0, right. And next clock it understand there is a C1 and it process D1. So, what is going to happen in this way? So, if you just put some intermediate buffer between these two process and such that whenever some this process all this process works independently, and whenever it produce some data, it will do not send that data directly to the next module, rather it just put it to the buffer in between, and there is a handshake method. So, there are two ways you have this process, two processes can handshake each other, is there will be two signal called empty and full, right. So, if it is full, that means the process the producer process understand that this buffer is already full and there is no space to write. So, it has to wait, right. So, now this process cannot go further until it finds some space to write the data in the intermediate channel or buffer, right. Similarly, the empty is important for the consumer process. So, consumer will always check whether this buffer has data or not. If the empty equal to 1, that means this buffer is empty, right. So, there is no data inside. So, this process has to wait, and this situation might occur because this process 1 may be very heavy, right. So, producing B0 might take say 5 cycle, whereas this process 2 can produce consume B0 and produce C0 maybe in 1 cycle. So, it is not that this all process will be equally take all the same number of cycles, but they may be basically not so I would say balanced. As a result, there may be some scenario can come in between when this consumer process has to wait for the data. And similarly, if the consumer process is very heavy process or there are a lot of computations are there, probably producer process has to wait in between until the consumer consumes some next data, right. So, this is how there is no kind of overflow or underflow can happen, or there is some inconsistency can happen, and the most important point is that just adding this buffer in between will enable this running this process independently and then run in parallel, right. So, that is the biggest advantage, right. So, by doing this, what we can do, we can actually achieve, we can improve the throughputs, that means we can produce output more frequently, and also probably the latency, because now the latency you can understand that because this all processes are now running in parallel, the overall time to compute the data will be much less, right. So, that is the what is the overall basic idea of the data flow optimizations. And given such behavior, whenever there is a so if you just have this kind of producer consumer functions, and if you just specify that HLS data flow, So, then the high level synthesis tool like Vivado HLS can understand this. So, probably I have to implement this as a data flow, and you can analyze whether this particular function can be implemented using the data flow, and if yes, what it does, it basically automatically generate this kind of hardware with all these handshaking signals, right. So, there will be some handshaking signal between these two process using this buffer between these two process and all. So, that there is no rest condition happen or deadlock happen or say starvation happen. So, everything will be controlled by this synchronization signal. So, the RTL that will be produced by the high level synthesis tool is in this form, and it is the execution of this is completely different from the actual C code, because in the C code it is going to execute it in sequentially, whereas here it will actually happen in parallel, right. So, now that we understand what is data flow and how this high level synthesis enable these things, right. So, the buffer that I talked about between two process can be implemented using FIFO and ping pong, right. So, there are two type of way it can be done. One is the first in first out, and another is the ping pong buffer. I am going to explain this how these things happen with examples. Okay. So, let us first take a very simple example where I try to produce and I try to convince you that how this data flow will improve the throughput and latency. Okay. So, the same example that I have taken arbitrarily. So, there are say 3 functions A, B, C, and then they are actually having a relation producer and consumer. You can see here that it produced I1 and I1 getting consumed here, it produced I2, I2 is getting consumed here. And you remember that it is not necessary that this function B can only take input from this function A, it can have some other inputs also like C, C is another input here, right. So, this can happen. So, now I have this, say let us say this function 1 takes a 3 cycle, right. So, this is 3 cycle 1, 2, 3, function take 3 cycle and function 2 takes 2 cycle, right. So, 3, 2, 3, okay. So, that means it is total 8 cycles. So, if you just execute this without data flow, it will actually implement in 8 cycles. So, it will create a module, module 1, module 2, module 3, and it will be, since there is no data flow, there is no synchronization between them. So, it will have a module 1 and module 2 will wait until this module 1 completes, and then it will be scheduled like that, right. So, first 3 o'clock module 1, next 2 o'clock module 2, and the next 3 o'clock module 3. So, it will take overall 8 cycles. Okay. Now, let us see I have applied data flow here, right. So, I just add the pragma HLS data flow. So, now see how the things will change. So, whenever there is a data flow, I already saw that it will create 3 modules, right. So, there will be 3 modules and there will be intermediate buffers, right. So, there will be intermediate buffers through which they will be synchronized and run them parallel. So, now I can run this 3 module A, B, C in parallel, right. So, what is going to happen? So, I will start the process function 1, right, and now because, so after sometime say after 1 clock it will produce some data, and immediately I can now start function B, because that is what I have said, ki first clock it will write something here, and then that in the next clock B can actually take this data and start this, and that is what is happening here. So, you see in the next here the B start only when a function A completes, right. So, when the function A completes, then only function B starts. Here function is B will go, A will going to complete here, but after 1 clock only, because some intermediate data is already available in the intermediate channel, function B can start execution, right. So, that is the important thing is happening here, and similarly after the next clock comes, B will produce something and function C can start his execution now. Okay. So, with this you can understand that now after 2 clocks, in from 3rd clock onwards, all these 3 functions are running on parallel, right. So, they are running on different data, but they are running in parallel, and I can see that after 5 cycle, because this function 3 will take 3 cycle and 2 more cycle here, after 5 cycle my first output will be produced. So, it is throughput become in every 5 cycle, every 5th cycle, here throughputs is every 8th cycle, right. So, the next output will come after 8 more cycle, right. So, they are in the non data flow version of the hardware, it will take the throughput will be 8, right, 1 in 8th cycle, here it is 1 in 5th cycle. Most importantly, since function 1 complete his execution here, Now, if you give the next set of data, in hardware it is not that you are only running for one data, right, continuous data is coming. So, it is a kind of stream of data is coming, one set of input comes, you process it, you get the output, then you give the next set of input, right. Since function A is completed here, I can now start the execution of the function A again for the next set of data, right. This is for the first set of data, right. So, there is set 1 and this is for set 2, right. So, this is the first set of data and this is second set of data. So, now I can start the whole process for the second set of data after third cycle itself. Here I cannot start it here because this function B will be completed and that is how it is scheduled. So, I can only start function A again here. So, that means here there is no even this for different set of inputs the function also not running, right. So, here immediately after function is completed, because now I can start function A on for the next set of data, and this is how the overall latency become. You can understand that the latency become so basically this latency become 3, right, because earlier it was 8, because I can now I can give input in every third cycle, right. So, this is the initiation interval or the kind of latency of the whole system, that earlier I can give the next set of data only after 8 cycles, now I am giving here after every 3 cycle, right. So, that is the advantage of having this. So, you can understand that this is much more efficient design, because here, because in hardware all modules in running parallel, and I am actually taking advantage of that using the data flow transfers. Okay. So, that is all about this data flow. Let me move on. So, as I mentioned that this with data flow it takes 8 cycles, here it is taking 5 cycles for throughputs, and so basically sorry. So, the latency, I mean I am little bit wrong there. So, that it takes 5 clock to produce the final output. So, latency is 5 and throughput is it actually I can start the process in every input. So, it is basically every 3, right. So, I mean I hope you understand that, and this is how this things is happening, that you are actually adding some channels here, right, and which is basically storing the intermediate data. Okay. So, let me try to now move on to this how this exactly it happened, right, how this channel works. And as I mentioned that there are two kind of channels is possible, ping pong and FIFO. Okay. So, let me start with this ping pong first. So, as I mentioned that this data flow architecture is something, it basically adds some FIFO or ping pong buffer in between, and there are some handshaking interface empty and full, and this by this handshaking interface now each task can run in parallel, right. And then it is also actually allow this better interleaving of the task. I can understand that now this all every clock all task is running, right. So, all task is running in parallel, but this kind of advantage coming with additional cost, that means you need this FIFO and ping pong implementation. So, you need more memory in between, because you need to put a large channel there. So, the size of this FIFO depends on the what is the maximum data can be written here, and you can have some calculation to identify what is the minimum size of this FIFO needed to communicate these two, but that some analysis needed, but in general it can be the maximum size of the kind of number of data it gets produced. So, this way this is the extra additional cost which does not need when you run it in sequential manner. Okay. But with this additional cost the benefits is huge. Okay. So, what I am going to do it now, I am going to take an example, this example, and I am going to talk about how this ping pong and then this FIFO style things get implemented with this example, right, and how that works actually. Okay. So, let us take the example here. I have taken a little bit bigger example. So, I have 4 modules, module 1, module 2, module 3 and module 4, and the data flow implementation is like this, right. So, what is happening here, you let us see. So, module 1 is taking inputs A and B, right. So, it is taking input A and it is producing 2 data B and C. If you see here, I am just taking a very simple so there is a loop inside the function module 1, and it is basically calculating array B and C, which is using this equation, right. So, whatever the AI, I am just multiplying with 9 and just multiplying with 2 to produce Ci. So, there are some all dummy operations just to represent things, and now this B goes to module 2. So, module 2 now consume B, produce D, and again there is a loop. So, in the loop I am just doing B star, right, Bi star to produce Di. So, it is basically making a square of Bi to produce Di, and then it is getting written into Di. Module 3 take this C which is produced by module 1. So, this produce B and C is getting consumed here and it is producing E using this equation, again it is doing C star, right. So, whatever the C is coming, Ci is coming, it will do a multiplication of that and it is producing E. And finally, module 4 is going to consume this D and E and it is producing F, it is just doing Di plus Ei to produce Fi. You can see these are, there are loops, right. So, all basically module have loops and they are actually taking the input and this is the data flow. So, in this case it is possible to apply data flow because there is no it is a forward flow and this is a producer consumer relations. Okay. So, now let us say I am going to implement this as a ping pong buffer. Okay. So, in the ping pong style, so the idea here is very interesting that between these two module you just put two buffers, okay, of the size of B and C, right. So, for example, here in this particular ping pong buffer I am going to the size will be of say the limit. So, the limit is say 10. Okay. So, that means, so this ping pong buffer has a array of size 10, right. So, what I am going to do here, I am going to put two buffers ping and pong, right. So, it is kind of even and odd, you can understand that even and odd. So, the basic idea is that it will consume one set of A module 1, right, it will produce a B and the complete B will be stored in this the first one. So, this is a even one and this is the odd one. Okay. And similarly, in this particular ping pong there will be two RAM, right. So, basically ping pong is implemented by a RAM and it will give two arrays, okay, of size. So, since the limit is 10, so sub size 10, right. It is I only, so here I need two copy of the buffer. So, the which is ping and another is pong kind of. Okay. So, this B is completely, so one set of A is taken, say A1 is taken which is size 0 to 10 and it will be written here. Okay. It will be processed A star 9 and it will be written here. So, this will be written and similarly from A it will produce the complete array C and it is going to be written here. Okay. And at that moment, so it will take 10 cycles say to complete this. So, first 10 cycle the other module will not start, right. So, here it is not that this the some data is already written, so I can start it. So, here the style is different, I am going to explain that. B will wait until the complete the even buffer is getting filled, right. So, this one set of data is written here. So, one set of data is now available and it is in the say even buffer. Okay. So, now for the next after 10 clock I assume that limit is 10. So, after 10 clock now B and C will start accessing this buffer and start working on it, right. So, what is going to happen from 11th clock onwards whatever the value B and C has first set of B and C, now this module 2 will consume B and module C is going to consume this C and it is going to be written in this buffer again. Here again there will be two copy. So, this E will be written in the even buffer now and here also the D will be written in the even buffer now. Okay. So, there will be two copy of the buffer which is very important and again this is say I am going to write these things data into the D into this buffer. At the same time from the 11th clock now this module 1 will take the next set of data, right. So, first set of data is already processed, now it will take the next set of data and it start writing the data in the next buffer, right. So, it will now start writing the things in the next odd buffer. Now, it will take the next set of data and it will going to write in the next buffer. So, this is say C2 and this is also say B2. You can understand that from after 11th clock module 1, 2 and 3 is now running in parallel. Okay. So, after 11 clock module 1 is working on the next set of data and module B and C is working on the first set of data and it is actually still and they are actually taking the data from the even RAM and this guy is writing the odd RAM. So, there is no conflict, right. So, there is no kind of problem or handshaking needed because they are actually writing two different data. Only thing is that now this module 4 cannot work because there is no data. So, unless the whole RAM is full it will not start. So, there is handsetting needed to say that the first my even buffer is now full, right. So, only then only I am going to start this module 4. So, from 10 to 11 to 20 now this module 1, 2 and 3 is running in parallel where this module 1 is writing to the odd buffer and module 2 and 3 is reading from the even buffers and producing the data and writing into the even buffer in D and E, right. So, after say 11 to 20 clocks, from 21 clock what is going to happen? So, now after this 11 to 20 all this data will be read, right. So, this buffer will become free now and this buffer will be full, because this this module 1 has written to the odd buffer. Similarly, after 20th cycle this buffer become available and this buffer will be full. So, now what is going to happen? Now, from the 21 clock to 30th clock, now this module 1 is going to take A3, the next set of data, and it is again going to write it in the odd buffer, right, because the odd buffer is free. So, basically the writing to this buffer will be alternate. For the first set of data it is in even, next set of data it is in odd, again is going to write in the even, next set of data will be in odd, and this is how things will work, right. So, similarly, now this module 2, because earlier it has taken from even data, now it is going to take it from odd buffer, right, the next set of data. So, it is going to take it from the odd buffer. Similarly, so here for the third set of data, module 1 is writing again to the odd buffer, this is writing to the odd buffer, and this module is again consuming from the odd buffers, and module 4 now can start taking data from this even buffer, right. And since in the next time, in the next clock, so this is going to be consumed from here, and so next time for the next set of data, module 2 is going to write the D into the next odd buffer, right, because now this buffer is free. So, it is again alternate way, it is going to write the data into the odd buffer module 2 and 3. So, now from 21 to 30 this cycle, you can understand this module 1, 2, 3, 4 all are running in parallel, right, but they are all running in different set of data, and since they are writing in either, so the reading and writing from this channel is happening either from so if the writing is going to happen in the even channel, reading is happening from the odd channel, right. So, there is no problem. So, they can actually run in parallel and they can when they can actually complete the things, right. So, you can understand that after certain period of time all this module will start running in parallel and they do not have to wait for others, because this complete data they can read and then it can actually run in parallel. Only thing is that if this module 1 is slower, because it is happening say two operations and here is only one operation. So, this module 2 might complete the processing of this odd data earlier and it has to wait, because this even channel is not full yet. Until that get full, it cannot start the next iteration. That is where the synchronization happen, but in Ping-Pong style. So, this is how, so this all model, so there is no interleaving happening. You can understand here that it is not that the for first whenever this the A0 is written, B0 is written, it start take the B0 and do that. So, it will actually wait for the completion writing of the odd even buffer, then only it will start. So, this is by managing this even odd buffer or ping-pong buffer here, I am actually implementing this whole process, and the advantage of having this is that here it does not need that your reading and writing sequence should be same. For example, this may be say from limit to 0, right. So, limit to 0 say, it is a different direction. Okay. So, the order of the writing can be different, because it is not that there is no once this guy is writing to this buffer, he is reading from this other buffer. So, it does not matter in which order they are writing. So, for ping-pong style, when the producing order and the consuming order is different, it is you have to implement the things in ping-pong style, right. But if the if the producing and consuming style is so order is same, then I can implement this as a FIFO. I am going to explain that. So, let me complete this execution with this animation here. So, let us say I have 3 set of data, and first set of data is A1, then say next set of data is A2 and third set of data is A3, and I am assuming the limit is 5 in this example. So, what is going to happen for the first 5 clocks, this A1 will be consumed and it will be processed and it will be written into this buffer B and C here. Okay. So, what is going to happen for the first clock, it will consume this and it is multiplying with 9 and it will be produced this data, and this data will be written in the even buffer, and this is basically say 5 into 2 is 10, 4 into 2 is 8. So, the first set of data will be multiplied by 2 and it will be written into this buffer, right. So, this is your even buffer, this is odd buffer, this is even buffer, odd buffer. So, this is for the first clocks, 5 clocks. Next 5 clocks is going to happen, it will now take A2, it will produce, it will multiply the element with 9 and it will produce this data, multiply the element with 2 and it will produce this data, and this will be written into this buffer, odd buffer, right, you can understand that. And similarly, at the same time you see here module 2 is now consuming from the even buffer this data, and it will do a square, and this data will be written into this in this even buffer. So, this all this now the execution of module 2, 3 and 1 is parallel, right, but they are writing reading and writing is happening from 2 different channels, right. So, the next clock, as I mentioned, now you are going to this particular module 1 going to take the A3 and it will multiply again with 9 and it will produce this data, and this will be written into the odd channel, and the even channel will be read by this module and this other channel. So, this is the odd channel will be written read by module 2 and module 3, and they will produce the data and it will be written into the buffers. And similarly, you can see here this module 4 is now consuming data from here and it is producing the data. So, it is all happening in parallel. You can see here I am running the animation again. As I mentioned, after some time the producing, so you see here module 1 is producing to this 2 buffer, module 2 and 3 is producing to this 2 buffer, and at the same time module 4 is also producing to the buffer. You can, I am running the parallel things again. So, this is going to write in the odd, this is consuming and writing in the even, and this is consuming from odd and writing into the even, right. So, the even and odd things is managing, right. So, ping and pong. So, this is what is the ping pong style, and if the access pattern is different, the only way you can actually realize this using ping pong buffer, and there are 2 copy of the buffer is needed. Okay. Now, I am going to take the same example, and fortunately in this example the order of access is same. You can understand that this will be produce B0, B1, B2, B3 and right there. So, B0 then 1 then 2 then 3, and here consumption is also 0, 1, 2 and 3, right. So, here the production of the producing order of B and consuming order of B is same. Similarly, for C, because the loops are all same size, right. So, the production and consuming order of C and D and E is also all same, right. So, in this case I can also implement the things with FIFO, okay. And to do that with data flow, you have to specify the HLS stream called pragma called stream, HLS stream. So, if you say that I want to make it a streaming application, then it will not implement that with a ping pong will be the default option, but if this producer consumer the access that producing order and consuming order is actually same, I can actually make the FIFO, and which is FIFO is something in which the arrays this buffer size will be not double, right. So, in ping pong there are 2 buffers is needed, in FIFO I need only 1 copy, and most importantly these modules can actually do not have to wait for the entire data to be produced. So, whenever one data is produced, because the consumption will be the same order, immediately that can be consumed. So, the much inner level this coarse grain parallelism can be happen, right. So, this now I can actually mixing the iteration of the modules also I can parallelize. Earlier it was, although they are running in parallel, but they are running on 2 different set of data, right. But here even I can, for the one set of data I can parallelize the 4 module and I can run all 4 module running for the same set of data even. Obviously, I can it should be parallelized for different set of data, but even within for one set of data also different iterations of these modules can run, right. So, I am going to explain this with the same example. So, let us take the same example and say initially I have this data array size 5, the same example. So, this is module 1, 2, 3 and 4, and this is a FIFO. So, FIFO transfer first in first out, that means whatever I am going to giving the input and the same order it will come out, right. So, it is kind of a queue, right. So, whatever the data you are writing, it will be consumed in that same order. Okay. So, now let us see. So, whenever my I equal to 0, so what is going to happen, the B0 and C0 will be produced, right. So, since it is 1, I am going to multiply with 9, so it will be 9, and it is 1, so it will be 2. So, this is my B0 and this is C0, it is produced, first clock is done. The next clock, now this FIFO will say it is not empty. So, B module 2 and 3 will understand, now my FIFO B and FIFO C is not empty. So, they can consume B0, right. So, what is going to happen now? So, they can now start their iteration 0, right. So, they can take now and module 1 now actually run the iteration 1, because first iteration is already done. Now, it will run the next iteration 1, and module 2 and 3 is now see can run in iteration 0. So, this was not happening in ping-pong. Ping-pong, it was the complete execution of module 1 is done, then only module 2 and module 3 are starting, right. So, it has to wait for first end cycle. Now, here after immediately after first clock, in the second clock, this module 2 and 3 can run their first iteration, whereas the module 1 will run for the next set of next data on 2. Okay. So, you see what is happening here now by animation very closely. So, you can see here now 2 and 9 will be consumed by module 1 3, they will produce 9 into 9 81 and 2 into 2 is 4. So, and similarly this module now taking the A1 which is 2 and will produce 9 into 2 is 18 and 2 into 2 is 4. So, they will produce this, and this will be written into this buffer, 18 and 4 will be written into this buffer FIFO B and C, and 81 will be written into FIFO D and 4 will be written into FIFO E, right. That is what is going to happen in, right. So, you can see here. So, they got written here. So, now after this clock, so this happened in the second clock, in the third clock it is going to happen. Now, this module 4 is can also run its iteration 0, right. So, now module 4 also can run in iteration 0, module 2 and 3 will run their iteration 1 and module 1 will run their iteration 2, right. So, it will now going to consume 3, it will consume this these 2 data and it will produce the D and D1 and E1, and this will take these 2 data and it will produce F0, right. It is actually consuming D0 and E0 and it is producing this, right. So, now you can see here after third clock, you can see here all these things is happening in parallel. This is very interesting, right. So, now so this is so it will take 3, right. So, it will take 3, it will produce 27 and 6, right, and this will take this 18 and it will do a square of 18 square is 324 and 4 square is 16, and that will be written here, and here it was 18 and 4 81 and 4 was there, it will consume and it will do addition, it will write into this, right. So, now you can see here all things are happening in parallel, right. So, this now this will be produced here and it will produce here. So, this way it will now run this A3, it will run the A2 I2 and this is run the I1, and this all running in parallel, right. So, this is how things will move on, right. So, this way it will can continue and finally, so you can see here. So, when once this you can see here, so whenever this is running the I equal to 4, that means the last iteration, 5th iteration, they are running I equal to 3 and this is running the I equal to 2. So, next this all set of data is actually processed, right. This is A0, A1, A2, A3 and A4. So, after this cycle this will complete the execution for the first set of data. They will have some still left and this will have to 2 more iteration left here, 1 more iteration left here, there is no iteration left, right. Now, next is important. Now, you see now for the it will now start the next set of data, it will now start accessing the next set of data, and this is actually working on the I equal to 4 for the first set of data. This is still working on the first set of data where I equal to 3. So, this I equal to 0 means it will now consume the next set of start consuming the next set of data, which is something say. So, this will it will be completed and it will start executing this, and if you do not have any data it will wait because there is no data. So, it will consume here, but in general. So, I just give the animation for one set of data, but in practice you can actually whenever this become I equal to 0 you give the next set of data and it will start consuming this data and it will start producing the next set of input. So, this is how FIFO makes sure that these modules actually can interleave their iterations also, right. They can parallelize their iterations as well, and they eventually actually can produce then can actually run for the same set of data. They can run parallel even for the same set of data, and finally, once the first set of data is over, now this module will start consuming the next set of data, and since this is order is different. So, they are going to be written in other places. So, whenever this guy is going to consume, it will consume the previous set of data, right. So, it will not actually create any problem. Okay. So, this is how this FIFO realize the data flow, and FIFO only can be applicable when the writing order and reading order is same. that means the producing and consuming order is same, then only I can implement FIFO. If it is not, if you ask the tool to apply FIFO, it will say it is not possible to apply FIFO because the produce order and consume order is different. So, then it will be implemented by Ping-Pong style, because in Ping-Pong style there are two buffers and the access is random, right. So, any order the producer can produce, consumer can actually consume in any order. So, you do not create any problem, but it need double buffer, right. So, here I need only one set of buffer. Okay. So, this way it will complete. So, I hope you understand what is data flow and how it actually improves the performance in the hardware, and it is actually truly hardware parallelism, right. So, although the actual C program is in sequential, but it actually extracts the parallelism among these models and actually enables a hardware which actually is truly parallel. Okay. So, there are some limitations in some cases where you cannot actually apply this data flow. For example, these are the case where you cannot actually apply. So, let me explain one by one. So, single producer consumer violation. So, the idea here is that if you produce say A here, and if you send this A to say process 2 as well as process 3, you are sending A. So, then it will not able to implement this. If you produce one data, it should be consumed only one consumer, not by multiple consumer. The best solution is that you copy this, right. So, you make it A1 and A2, you put A1 here and you put A2 here, then it will work, right. So, the idea is that one data cannot be sent to two consumer. Okay. Bypassing task is something like this. So, if you have say this is a process 1 and there is a process 2 and there is a process 3 and it is producing say B and it is consumed by here, and it is say producing A and it is consumed by process 3. So, this is not allowed. So, it is basically should be a forward flow, it should not bypass any of the process. So, if it is there, you cannot implement this data flow, right. So, this is what is the bypass task. Feedback between task is not, obviously cannot work on that. So, if there is some C is getting produced and it is consumed here, right. So, then it cannot run in parallel, because there is a complete dependency, right, until these things is done, and then only you can start the next iteration. So, there is no point of implementing data flow. So, if there is a feedback, you cannot implement data flow. Okay. And then conditional execution of task is, obviously you understand that if say some condition is true, then only you do the data flow, otherwise you do not do that. That also is not supported. In that case, you cannot actually implement data flow. And you as the example I have taken, there is a loop, right, and if the loop should be you could not have a break exit in the loop, right. So, if there are multiple exit, you cannot implement data flow, because this data flow needs lot of synchronizations, and once you have this multiple exit, the synchronization become too complex, and the modern day high level synthesis tool still will not be able to handle such complex scenarios. Okay. But if it is forward flow, as I mentioned, there is these conditions are not there, then then you can actually implement this using data flow, and data flow gives you a efficient hardware. Okay. So, with this I conclude today's class. In the next class, I will take another interesting topic, that your actual code may not be in the way it is written, that your data flow cannot be applied, but we can actually rewrite the code to make it efficient for data flow implementation, because the data flow implementation gives a huge performance benefit. And so, basically in modern day, if you think about this machine learning algorithms, if you understand this machine learning algorithm or image processing algorithms, where there is a lot of loops and lot of data is getting produced and is get consumed by the next one, right. So, the idea here is that can I rewrite my code somehow, if you take the original code, it is may not be, there is no data flow, but I can actually rewrite my code such that I can actually create the data flow instances, and then I can actually run these modules in parallel, right. So, that is something a very interesting area of research, because if you just can do this data flow implementation, that's give you a huge benefit, right. So, in next class I am going to take two such examples, and I am trying to show that the original behavior is not supporting data flow, but this is how we can modify, and then after the modified, the data flow will be supported and you get the maximum benefit. Okay. Okay. So, with this I conclude today's class. Thank you.